Zach West of the USA has built an electrolyzer which powers a 250cc four-stroke motorcycle which he has run on public roads in America. Zach estimates that the HHO gas output of his electrolyzer is 17 litres per minute. His design of electrolyzer is interesting both for its simplicity and its high rate of gas output. The increased gas volume which would be produced if this design were adapted for and driven by a 12-volt electrical input, and that could make the general design very useful indeed. The method which Zach uses is somewhat unusual, as he manages to bleed off and discard most of the oxygen produced. This means that the remaining gas is mainly hydrogen, which is far less reactive than an HHO gas mix, which is already in the perfect proportions for combination back into water, and because of that is so highly reactive. Instead, the resulting gas can be compressed reasonably well, and Zach compresses it to 30 pounds per square inch in a storage container. This helps with acceleration from stationary at traffic lights. Zach uses a simple modular system of construction where a series of coiled electrode pairs are each placed inside an individual length of plastic pipe. This is a design which is neither difficult nor particularly expensive to build. In overall broad outline, Zach's electrolyzer is fed water from a water tank to keep it topped up. The electrolyzer box contains several pairs of electrodes which split the water into hydrogen and oxygen when fed with pulsed electrical current generated by the electronics, which is powered by the electrical system of the motorcycle. The gas produced by the electrolyzer is fed to a dual-purpose bubbler, which prevents any accidental igniting of the gases from travelling back to the electrolyzer, and in addition removes most of the oxygen from the gas by acting as a gas separator. The arrangement is like this. You have a water tank with an airtight cap feeding the electrolyzer, which is driven by the electronic pulsar board, which is powered by the 6-volt system of the actual motorcycle. The gas produced is fed down into this bubbler unit, which has got two coils of wire included in the feed to the electrolyzer itself. So the pulsing voltage going to the electrolyzer passes through these two coils of wire, which form electromagnets, and the way that they're organized is that they are wound in opposite directions, where the end of the first coil becomes the start of the second coil. Anyway, the way that it's arranged is that you have a north pole on one side and a south pole on the other side, and that alternates with the pulses going to the electrolyzer. The gas output is separated by the magnetic field to a certain degree, because the oxygen atoms have got a negative charge and the hydrogen atoms have got a positive charge, and that organizes it so that the oxygen tends to reach the surface on this side of a partition, and the hydrogen tends to reach the output on the left-hand side of that partition, and that goes then to the tank, whose pressure is then allowed to build up to as high as 30 pounds per square inch. That passes then to the ordinary throttle of the motorcycle, and what's passed through is mainly hydrogen with some oxygen mixed in it, but not nearly enough to convert back to water. So the oxygen in the air is used as normal in the motorcycle combustion arrangement. The hydrogen gas output from the electrolyzer is not going directly to the engine, but instead it goes through the pressure tank, which is allowed to build up to 30 pounds per square inch before the engine is started. The majority of the oxygen produced by the electrolysis is vented away through a 30 pounds per square inch one-way valve, which is included to keep the pressure inside the bubbler and the electrolyzer at the 30 pounds per square inch level. That pressure is excessive for a high performance electrolyzer, which produces HHO, which is highly charged electrically, and so the HHO produced that way will ignite spontaneously when compressed to about 15 pounds a square inch due to its own electrical charge. In this simple DC electrolyzer, the HHO gas is mixed with quite an amount of water vapor, which dilutes it and allows some compression. The water supply system operates by having an airtight supply tank positioned at a higher level than the electrolyzer. A small diameter, that's 6 millimeters or a quarter inch, plastic tube coming from the supply tank feeds water through the top of the electrolyzer and straight down, terminating at exactly the electrolyte surface, the level which is wanted in each of the electrolyte tubes is organized in that method. When the electrolysis lowers the electrolyte level below the bottom of the pipe, bubbles of gas pass up the tube, allowing some of the water to flow from the tank to raise the electrolyte surface back to its design level. There's the bottom of the actual tube supplying the water, and that is the top of the electrolyte. The electrolyte is typically 28% potassium hydroxide. The potassium hydroxide is a true catalyst, and as a result it doesn't get used at all in the electrolysis process. It is possible for some of the potassium hydroxide vapor to go out through the gas vent from this particular electrolysis unit here. This is one of the units inside the electrolyzer, of which there are 8, and it is an unusual way of organizing the particular electrolyzer. What he has done is he has taken thin pieces of stainless steel, that's 316L grade stainless steel, and this shim stock, which the very thin steel is called, is springy, and it's wound round with spacers. The spacers maintain the gap between the successive pieces of the metal as the turns continue round and round inside this plastic tube, which forms effectively its own single electrolyzer. As the springy metal pushes outwards in an attempt to straighten up, the spacers keep the electrodes evenly separated along their whole length by inserting 1/8 inch or 6 millimeter thick vertical spacer pieces. The connection to the plates are made by drilling a hole in the corner of the plate and inserting the wire through the hole and twisting it back around itself if you're using thin wire. The wire that Zach uses though is American wire gauge 12, which is 2 millimeter thick metal core inside the cable, and you can make a wire-to-wire solder joint by connecting both sides of the wire going through the steel plate. The joint is then insulated with silicon or other suitable material, and it's essential that the joint does not short circuit to the other electrodes, even though the electrodes are closely spaced. The solder will not take to stainless steel, and it's difficult to make a good connection, so you are in effect soldering the copper wire to itself to form a loop which is tight against the stainless steel plate. An unusual feature of this design is that each of the electrode pairs is effectively a separate electrolyzer in its own right, and it's capped top and bottom and effectively physically isolated from the other electrodes. The water feed comes through the top cap, which has a hole drilled in it to allow the gas escape. The electrical wires have a 2mm diameter and are fed through the base and sealed against leakage of the electrolyte. Each of these units has some electrolyte stored above it, so there's no chance of any part of the electrolyte surface not being able to generate gas. There's also a large amount of freeboard above the electrolyte to contain splashes and sloshing without being able to escape from the container. The end caps are standard PVC caps available from the supplier of the PVC piping, as the PVC glue is used to seal them to the pipe. 8 of these electrodes are placed, or perhaps I should say, eight of these electrolyzers are placed in a simple case and connected together in pairs like this. You have the two sides for the minus connected together, and you have the two sides for the plus connected together. The pairs are wired in as pairs of cells together. These pairs of pipe enclosed electrode spirals are then connected in a chain inside the electrolyzer as shown here. You've got 4 pairs of 2 electrolyzer tubes connected together in series. That means that the voltage supplied to this overall group, which is about 7.3 volts typically for a motorcycle when the charger is running, when the actual engine of the motorcycle is running, is divided by 4 to give the voltage across each of the pairs. So you're talking about somewhat more than 1.5 volts, which would be 6 volts. It's less than 2, which would be 8 volts. It's not actually far less than 2 volts on each of these pairs of cells. Now, the system that operates is you have the 6-volt battery and motorcycle generator supplying power through a 30-amp fuse, and a relay which ensures that the electrolyzer does not operate when the motorcycle engine is not running. It feeds on to a pulse width modulator pulsing system. These are common little boards which are readily available commercially. They're very simple, very straightforward, and the frequency can be adjusted, and quite often the length of the pulses for any given frequency can be adjusted. That's called the Mach space ratio. That gives you very considerable control over what's being fed on. The power then goes on through the 2 coils of wire, which effectively help to separate a lot of the oxygen from the oxygen-hydrogen mix. The electrical connection then goes on and through the electrodes and back then to the 6-volt battery again. This is the overall system. It's very straightforward, it's very simple, and it's not that difficult to understand. Many years of experimentation and testing have shown that 316L grade stainless steel is the most suitable material for electrodes. But surprisingly, stainless steel is not highly electrical conductive, as you would expect, because you've been taught from a young age that metals conduct electricity and non-metals don't conduct electricity. Well, that's technically true, but in the case of stainless steel, while it does conduct electricity, it doesn't conduct it very well. That's why wires are never made of stainless steel. They always have a core of something much more conductive, typically copper, and ideally copper with lots of little strands to increase the surface area, because the bulk of current flow in a copper wire flows along the surface area of the conductor itself. But the preparation of the plates is one of the most important steps in producing an electrolyzer which works well. This is a long task, but it is vital that it is not skipped or skimped or hurried in any way. Surprisingly, brand new shiny stainless steel is not particularly suitable for use in an electrolyzer, and it needs to receive careful treatment and preparation before it will produce the expected level of gas output. The first step is to treat both surfaces of every plate to encourage gas bubbles to break away from the surface of the plate. This could be done by grit blasting, but if that method is chosen, great care must be taken that the grit used does not contaminate the plates. Stainless steel is not cheap, and if you get grit blasting wrong, then the plates will be useless as far as electrolysis is concerned. A safe method is to score the plate surface with coarse sandpaper. This is done in two different directions to produce a crosshatch pattern. This produces microscopic sharp peaks and valleys on the surface of the plate, and those sharp points and ridges are ideal for helping bubbles to form and to break free from the plate. If when you're doing hand sanding, the sandpaper is drawn across the plates in one direction only and not backwards, as the backward stroke always destroys the perfectly good ridges created on the forward stroke. Also, you only need 2 strokes in one direction before turning the plate through 90 degrees and completing the sanding of that face of the plate with just 2 more strokes of the sandpaper, again with no backstroke. Always wear rubber gloves when handling the plates to avoid getting finger marks on them. Wearing these gloves is very important, as the plates must be kept as clean and as grease free as possible, ready for the next stages of their preparation. Any particles created by the sanding process should now be washed off the plates. This can be done with clean tap water, provided you're not in a city. City water, due to all the chlorine and other chemicals added to it, makes it unsuitable for this washing process. But the final rinse should always be done only with distilled water. While potassium hydroxide and sodium hydroxide are the very best electrolytes, they need to be treated with care. The handling for each is the same. Always store in a sturdy airtight container which is clearly labelled Danger Potassium Hydroxide. Keep the container in a safe place where it can't be reached by children, pets, or people who don't take any notice of the label. If your supply of potassium hydroxide is delivered in a strong plastic bag, then once you open the bag, you should transfer all its contents to a sturdy airtight plastic storage containers, which you can open and close without risking spilling the contents. Hardware stores sell large plastic buckets with airtight lids that can be used for this purpose. When working with dry potassium hydroxide flakes or granules, wear safety goggles, rubber gloves, a long sleeve shirt, socks and long trousers. Also, don't wear your favorite clothes when handling potassium hydroxide solution, as it's not the best thing to get on clothes. It's also no harm to wear a face mask which covers your mouth and nose. If you're mixing solid potassium hydroxide with water, always add the potassium hydroxide to the water and not the other way round, and use a plastic container for the mixing, preferably one which has double the capacity of the finished mixture. The mixing should be done in a well ventilated area which is not drafty, as air currents can blow the dry potassium hydroxide around. When mixing the electrolyte, never use warm water. The water should be cool, because the chemical reaction between the water and the potassium hydroxide generates a good deal of heat. If possible, place the mixing container in a larger container filled with cold water, as that will help to keep the temperature down. And if your mixture should boil over, as it might be thought of, it will contain the spillage. Add only a small amount of potassium hydroxide at a time, stirring continuously. And if you stop stirring for any reason, put the lids back on all containers. If in spite of all precautions you get some potassium hydroxide solution on your skin, wash it off with plenty of running cold water and apply some vinegar to the skin. Vinegar is acidic and will help balance out the alkalinity of the potassium hydroxide. You can use lemon juice if you don't have vinegar to hand, but it is always recommended to keep a bottle of vinegar handy. Plate cleansing is always done with sodium hydroxide. Prepare a 5% to 10% by weight sodium hydroxide solution and let it cool down. A 5% solution by weight is 50 grams of sodium hydroxide in 950 cc's of water. A 10% solution by weight is 100 grams of sodium hydroxide in 900 cc's of water. As mentioned before, never handle the plates with your bare hands, but always with clean rubber gloves. A voltage is now applied across the whole set of plates by attaching the leads to the outermost of two plates if you have a set of plates aligned in a row with spaces between them. This voltage should be at least 2 volts per cell, that is, between the plates, but it should not exceed 2.5 volts. Maintain this voltage across the set of plates for several hours at a time. The current is likely to be 4 amps or more. As this process continues, the boiling action will loosen particles from the pores and surfaces of the metal. This process produces HHO gas, so it's very important that the gas is not allowed to collect anywhere indoors, such as on ceilings. After several hours, disconnect the electrical supply and pour the electrolyte solution into a container. Rinse out the cells thoroughly with distilled water. Filter the dilute sodium hydroxide solution through paper towels or coffee filters to remove the particles. Pour the dilute solution back into the cells and repeat the cleaning process. You may have to repeat the electrolysis and rinsing process many times before the plates stop putting out particles into the solution. If you wish, you can use new sodium hydroxide solution each time that you do the cleansing, but please understand that you can go through a lot of solution just doing this cleaning stage if you choose to replace it every time. When cleansing is finished, typically 3 days of cleansing, do a final rinse with clean distilled water. It's very important that during cleansing, during conditioning, and during use, that the polarity of the electrical power is always the same. In other words, don't swap the battery connections over, as that destroys all the preparation work and requires the cleansing and conditioning processes to be carried out all over again. Using the same concentration of solution as in the cleansing, fill the cells with dilute solution. Apply about 2 volts per cell and allow the unit to run. Remember that good ventilation, and perhaps very good ventilation, is essential during this process. As water is consumed, the water levels will drop. Once the cells stabilize, monitor the current draw. If the current draw is fairly stable, continue with this conditioning phase continuously for 2 to 3 days, adding just enough distilled water to replace what is converted to gas. If the solution changes color or develops a layer of crud on the surface of the electrolyte, then the electrodes need more cleansing stages. After 2 to 3 days of run time, pour out the dilute sodium hydroxide solution and rinse out the cells thoroughly with distilled water. The actual running solution for your electrolyzer will be typically 28% by weight of potassium hydroxide, mixed up obviously with distilled water. The construction which ZAC has used is very sensible, using readily available low-cost PVC piping. The spiral electrodes are inside 2-inch diameter, that's 50mm pipe, and ZAC says that the bubbler is also 2-inch diameter PVC pipe. I seriously doubt that a 2-inch diameter bubbler will be able to handle a flow as high as 17 liters per minute, which is a substantial amount of gas flow. Also, you want the bubbles in the bubbler to be small in order that the gas comes into good contact with the water. Consequently, using more than one bubbler, where the diagram shows just one, would be sensible. At this time, ZAC only uses one bubbler, but a second one is highly desirable, located between the storage tank and the engine and positioned as close to the engine as possible. This extra bubbler does 2 things. Most importantly, it prevents the gas in the storage tank from being ignited by a backfire caused by a valve sticking slightly open, and secondly, it removes every last trace of potassium hydroxide fumes from the gas, protecting the life of the engine. This is a big gain for such a simple addition. The gas storage tank is also made from PVC pipe, this time 4-inch or 100mm diameter. It's 14 inches, which is 350mm long, with standard end caps fixed in place with PVC glue, as shown here. This is a compact and effective arrangement, well suited for use on a motorcycle. The majority of this extra equipment can be mounted in bike panniers, which actually is a neat arrangement. The electric drive to the electrolyzer is from a pulse width modulator, commonly known as a DC motor speed controller. This is a picture of the one that ZAC used. You can get these quite readily on eBay and probably in model shops as well. A fuse protects against accidental short circuits, and a relay is used to control when the electrolyzer is to be producing gas. The connecting wire is number 12 AW American wire gauge, which is standard wire gauge 14 elsewhere. It has a maximum continuous current capacity of just under 10 amps, so although the current peaks may be 20 amps, the average current is much lower than that. The DC motor speed controller should be able to supply 20 amps of current. A very interesting feature of ZAC's design is the bubbler, which manages to remove most of the oxygen produced in the HHO gas mix. Two electromagnets are positioned outside the bubbler. They're located 2.5 inches or 65 millimeters above the base of the bubbler itself. These electromagnets are connected as part of the electrical supply to the electrolyzer, and these cause most of the oxygen and hydrogen bubbles to separate and exit the bubbler through different pipes. There is a divider across the bubbler to assist in keeping the gases from mixing again when they get above the water surface. The bubbler also washes most of the potassium hydroxide fumes out of the gas as the bubbles rise to the surface, protecting the engine, as these fumes have a very destructive effect on engines. The objective with any HHO system is to have the minimum amount of gas between the bubbler and the engine in order to block the ignition of the gas in the unlikely event of a backfire. In this system, the gas storage tank contains a very large amount of gas, though admittedly it's not full of HHO gas thanks to the electromagnetic separation system. That electromagnet separation system appears to work quite well, but nevertheless it would be most advisable to have a second bubbler between the gas storage tank and the engine, positioned as close to the engine as possible. The HHO gas produces a very high speed shock wave, and if it is ignited. So the bubbler itself needs to be a strong construction to withstand this. No pop-off bubbler cap or blowout device acts fast enough to contain a HHO shockwave, so make the bubbler housing strong enough to withstand the pressure wave. ZAC's electrolyzer arrangement is like this. You have an airtight cap on a rigid water tank which feeds through a small plastic tube to each of 8 spiral wound electrode containers to form the overall full electrolyzer. The tube then comes from there to the first bubbler, which has electromagnets on it which pulse as do the entire wiring system and general supply pulses continuously due to the way that the pulse width modulator pulses the current. The current is not connected continuously. In most instances it tends to be off more of the time than it's actually on. That's the general arrangement for the gas operation. That's the way that the gas works itself. It must be realized that the water tank, electrolyzer, bubble separator and hydrogen holding tank all operated at 30 pounds per square inch. This means that each of these containers must be robust enough to withstand that pressure. You notice that this position here is where the 30 pounds per square inch check valve or one-way valve is located. So everything to the left of there is at 30 pounds per square inch once the system is running properly. It should be said, though it's fairly obvious, that it is essential to have that 30 pounds per square inch one-way valve. He can be allowed, if you wish, just to have the O2 vented directly, but it's essential to have, if you're going to do that, it's still essential to have the 30 pounds per square inch check valve there. The bubbles of gas escape into the water tank every time the water level drops down and the water goes in to feed the actual electrolyzer itself. The water drips down, but you get reverse pressure gas going back up that tube. I know it's a small tube, it's only 6 millimeters or quarter inch, but you still can get a bubble going up it. The electrolyzer itself has a potassium hydroxide solution in it. The electrolysis produces a mixture of hydrogen, oxygen, dissolved gases, air, potassium hydroxide fumes. When the system is being used, the water in the bubbler washes out most of the potassium hydroxide fumes, and in doing so it gradually becomes a dilute electrolyte itself. Potassium hydroxide is a true catalyst, and while it promotes the electrolysis process, it does not get used up during electrolysis. The only loss is to the bubbler. Standard practice is to fill the bubbler with fresh water from time to time. Potassium hydroxide has been found to be the most effective catalyst for electrolysis, but it has a very bad effect on engines if it's allowed to enter. The first bubbler is very effective in removing the potassium hydroxide fumes, but many people prefer to take the scrubbing process a step further by placing a second bubbler in the line, in this instance between the hydrogen pressure tank and the engine. With two bubblers, absolutely no potassium hydroxide fumes reach the engine. When running with HHO gas as the only fuel, it's essential to adjust the timing of the spark so that occurs after top dead center. The timing on this motorbike is now set at 8 degrees after top dead center. This electrolyzer is designed to run off the nominal 6 volts of a motorcycle electric system, and that actually is at 7.3 volts when the engine's running. ZAC uses the very simple method of allowing excess gas, that is oxygen, to be vented via the oxygen valve if gas production exceeds the requirements of the engine. This now needs a caution. This electrolyzer is not a toy. If you make and use one of these, you do so entirely at your own risk. Neither the designer of the electrolyzer, the author of this document, or the provider of the internet display are in any way liable should you suffer any loss or damage through your own actions. While it's believed to be entirely safe to make and use an electrolyzer of this design, provided that the safety instructions shown in this document are followed, it is stressed that the responsibility is yours and yours alone. An electrolyzer should not be considered as an isolated device. You need to remember that both electrical and gas safety devices are an essential part of any such installation. The electrical safety devices are a circuit breaker, as used by any electrician when wiring a house, to protect against accidental short circuits, and a relay to make sure that the electrolyzer does not operate when the engine is not running.